last forever. Whatever.
Although there's a ton of excitement these days around LLMs and AI agents, I'm more excited about the recent innovations in text embeddings. We saw these in the previous video of this series where we used text embeddings to implement a RAG system to improve an LLM. In this video, I'll discuss text embeddings in greater detail and share two simple yet high value use cases, namely text classification and semantic search. And if you're new here, welcome. I'm Shah. I make videos about data science and entrepreneurship. And if you enjoyed this content, please consider subscribing. That's a great no-cost way to support me in all the videos that I make. There's a fundamental challenge in trying to analyze text. Put one way, text isn't computable, meaning we can't do math with text in the same way that we do with numbers. For example, say you go to a networking event and you're talking with other professionals in the data space. If you wanted to summarize the typical height of every person at the networking event, this is something that would be pretty straightforward. All you would need to do is measure the heights of everyone at the networking event, and then you can summarize these heights using something like an average. And this is something that you can easily compute using a calculator, Excel, or your favorite programming language. However, if you have the job descriptions of everyone at this networking event, summarizing everyone's roles wouldn't be as straightforward because there's no Excel function or mathematical operator that allows you to put in text and generate a summary. And so this is where text embeddings come in. And put simply, text embeddings translate words into numbers. So if we have those same job descriptions from the networking event, translating these descriptions into text embeddings would look something like this. For every single description here, we would map it to a set of numbers. But these aren't just any set of numbers. These are numbers that capture the inherent meaning of the text. In other words, text embeddings translate words into meaningful numbers. And one way we can see this is take all those numbers from the previous slide and use them to visualize all the job descriptions. And so that would look something like this, where the numbers that we generated in the text embedding define the location of each person's job description. We can see the data analyst in retail with 5 years of experience is somewhere here, and they are located next to a freelance data visualization specialist with 4 years of experience. However, these people are relatively far away from this guy who is a data architect with 15 years of experience. And so this is the way that text embeddings capture the meaning of the underlying text. Namely, job descriptions that are similar will be located close together, while job descriptions that are very different will be located far away from each other. From this view, the BI analyst in hospitality early career is very different than the data architect with 15 years of experience. So if you've used ChatGPT in the past, the thing that might come to mind is, Shah, why should I care about these text embeddings and translating text into numbers? Can't I just pass all my text to ChatGPT and have it figure out what I'm trying to do? And the answer is yes. There are many tasks that don't require these text embeddings, and they're much better suited for ChatGPT. For example, if we wanted to summarize the 8 job descriptions from the networking event, it would actually be super simple to pass all these to ChatGPT and generate a summary. However, if you have a use case that's not just some one-off low-stakes task, but it's something you're trying to integrate into your product or a website or some broader production-level software system, then you'd probably want to at least consider using text embeddings before running off and building an AI agent. And the reason is, if we're talking about AI assistants, it's really the early days for this type of technology, and there are still a lot of things that we don't understand about using these large language models in this way. Another downside of using an AI assistant for your use case is that there's a major computational cost associated with running these large-scale models. Another downside is the inherent security risks that come with building LLM-based applications. And so there's a nice list of top 10 LLM security risks at reference number 3, which I recommend you check out. For example, these are things like prompt injection, which are maliciously crafted prompts which get the LLM to expose private or confidential data or disrupting some expected decision-making decision-making pipeline. Finally, responses from these LLM-based systems might be unpredictable and prone to hallucinations, where the system generates fictitious or unhelpful information. On the other hand, text embeddings have been around for decades, and there are several past example applications that we can look to help guide future applications and use cases. Another upside of using text embeddings is that they have a much lower computational cost and thus financial cost than using an entire large language model. Another is that there are far fewer security risks associated with using an embedding model compared to a large language model that users can access through a chat interface. Finally, the responses are more predictable because every word or piece of text will generate a deterministic set of numbers. So there's no randomness in this process. Now that we have a basic understanding of what text embeddings are and why we should care about them, let's see how we can use them for a practical use case. The first use case I'm going to talk about is text classification, which is the process of assigning a label to a piece of text. For example, if we were to take all the people from our networking event and their associated job descriptions, a classification task could be trying to determine which people are data analysts and which people are not data analysts based on their respective job descriptions. So that might be pretty simple here, because anything to the left of this blue line we could label as a data analyst, and anything to the right we could label as not a data analyst. However, text classification is a broadly applicable use case. Some other situations might be classifying emails as phishing attacks versus not phishing attacks, or classifying credit applications as fraudulent or not fraudulent. And the list goes on and on and on. With this high-level understanding, let's see what text classification with text embeddings looks like in code. So in this example, I'm going to take a data set of resumes and try to classify them as either data scientist or not data scientist based on the content of each resume. The code in the data set for this example is freely available on the GitHub repository linked here. Feel free to steal this code as a jumping off point for your own use case. So the first thing we're going to do is import some helpful libraries. Here we're going to use OpenAI's text embeddings. To use OpenAI's embedding models, we'll need to use their API, which requires a secret key. If you're unfamiliar with the OpenAI API,
no, man.
repository linked here.
Arch Linux. It's booting. Guys, I see it. I see things happening. Oh my gosh. I don't even want to talk to another woman ever in my lifetime. I know why it does this to a man now. I can feel the configuration surging. Surging through the fingers right now. It also can't read, like me. I don't know what happens here, okay? It just, there's this thing that it does for 60 seconds where it can't read, you know, so, like, I can't be upset about it because, like, I can't read either. So, why would I be upset if we're the same? My keyboard, is that the problem? I could unplug it. I don't know why it's slow, okay? Unplug USB. Unplug. Plugged. Oh my gosh. I see a user. Oh my gosh. I see a user. I see a user. I see a user. Okay. 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 Hold on. I gotta plug it. I gotta plug back in. What's happening? We're in. YouTube just really is missing out on this. YouTube has no idea how awesome this actually is. YouTube just thinks this is just you don't even know YouTube. Okay, it says an error over here. Okay, I'm not gonna lie to you. Ground control Major Tom. I don't know how to open up anything. Super Q for Kitty. We did that. Okay, I don't like that, but okay, that's fine. Super M to exit. Okay, that's fine. Can I click you? How do I make you go away? Okay, what's the play here? Okay. I mean, I could get used to that. Okay, I could get used to that. Edit the config to get rid of this message. Okay, where's this thing at? Vim. Where is it? It's under. Dude, I hate using QWERTY. Config. Hyper. Let's see. Edit the config file to get rid of this. Okay. So nice. Oh yeah. Depends on.
Yeah.
In this course, I'll teach you how to use vector search and embeddings to easily combine your data with large language models like GPT-4. First, I'll teach you about the concepts, and then I'll guide you through developing 3 projects. In the first project, we'll build a semantic search feature to find movies using natural language queries. For this, we'll use Python, machine learning models, and Atlas vector search. Next, we'll create a simple question answering app that uses the RAG architecture and in this course, and we'll build a semantic search feature.
यार सब लोग साला यूज कर रहे हैं man, shoot. पानी का बोतल नहीं लाओगे क्या भाई? पता चलेगा चुट जाएगा.
In last video, we looked at bidirectional RNN. Today, we are going to talk about how you can convert words into numbers. When you're dealing with any natural language processing task, your input is text, and machine learning models can't understand text, so you have to get it converted into a number. Let's take the example for the game of cricket. Let's say you're building an NLP model for this game, and the task you have in hand is to recognize entities in a given sentence. For example, here, Dhoni would be a player name, India would be a team name, and World Cup would be a tournament. Similarly, you can have a different statement and you want to identify the entities. So this is called name entity recognition. And based on previous video, you can build an RNN that looks like this. But if you observe carefully, there was one big problem when I covered NLP task for RNN in my last video. And the problem is the input. The machine cannot understand text. See, here the input is Dhoni, Goa, Team India, whatever. The machine learning model can't understand text. We have to convert that into a number. So how do you do that? So you see, you have a text. You have to put this extra layer as an input, and you have to convert all these words to numbers. Now let's say for training the model, you scrap the internet. Okay, so you go to websites like ESPN, Cricinfo, Wikipedia, and so on. You try to grab all the articles, to build your language model, and you build a vocabulary out of it. So vocabulary is nothing but list of words. So let's say this is your vocabulary. You start with Aksar is the name of the player, Dhoni is the name of the player, Zimbabwe is the name of the team, and so on. Let's say my vocabulary has 50,000 words. You can assign unique number to each of these words, and then you can use those numbers as an input to your RNN. For example, Dhoni has number 7, so see, use 7 here. Now, that's your option number 1, basically.
Direct key mapping.
Converting words into unique numbers based on your vocabulary. But there are issues such as the numbers are random. They don't capture the relationship between two words. For example, in this particular case, Dhoni's number is 7, Aksar's number is 2. Dhoni and Aksar both are players, so maybe these numbers should be similar, but they are far apart. Whereas Ashes is the name of the tournament, it is more near to Akshar. So these kind of random numberings cannot capture the similarities between the words. So then the second option you have is one hot encoding. If you've seen my machine learning videos, you might have seen one hot encoding tutorial.
भूख नहीं ने लगा है बात तो ये भी है कौन खाएगा भाई अभी बोतल ख़त्म जाएंगे अब बाद में मतलब आधा बोतल ख़त्म आधा बोतल ख़त्म
Which is basically you take all your words, and when it is ashes, for ashes you put 1, remaining words you put 0, and you get a vector. For example, the vector for Aksar would be 0, 1, 1. So wherever Aksar appears, you put 1, remaining numbers are 0. So this is a very popular approach in machine learning. But this also have a couple of issues. Like number one issue is obviously they don't capture the relationship, because see, again, there is no relationship established. If I don't tell you the words, if you're just looking at these numbers, you can't tell if two words are same, like banana and grapes, for example. These are the two fruits. So if you have these two fruits, maybe you want their vectors to be a little similar. The second problem is it is computationally inefficient. If your vocabulary has 50,000 words, for each word you get a vector whose size is 50,000. Often in machine learning problems, the number of words could be in millions or trillions, millions of billions, maybe not trillion, or it could be trillion in future, but you get the point. So the computational cost is very, very high. So the third option you have is using word embeddings. Word embeddings allow you to capture relationship between the two words. Let's say, how do you capture similarities between two words? So let's take the example. In order to explain how word embedding work, I want to take you back to your first machine learning problem, which is predicting home prices. So if you have two homes and you want to, let's say, figure out if these homes are similar or not, how can you do that? Well, you look at the features of the home. What are the features? It's simple, right? Like the bedrooms, area, bathrooms, and so on. So if you look at these two homes, the bedrooms are same, area is almost same, 1700 versus 1850. Bathrooms are also kind of near to each other. So then we can say that these two homes are similar based on the features. If I have a third home, let's say big mansion, which is very big home, and if I look at the features of this home, the feature vector would be 10, 7500, and 2. And when I compare this vector with this vector, I will obviously figure out that these two homes are not similar. Can we apply similar concepts to the words? Let's say these are my words, Dhoni, Cummins. I put just pictures for the reference. Otherwise, we are comparing just the words, okay? So Dhoni, Cummins, who is an Australian player, and Australia, which is the name of the country. How can you compare these three words? Now, as a human, we know that Dhoni and Cummins are similar because these are players, names of players. But Australia is not similar because it's the name of the country or name of the team. So then, just think about, is there a way to retrieve features from these words? If you think hard, you might be able to come up with some features such as person, whether the person is healthy or fit, location, has two eyes, has government. So in the case of Dhoni, yeah, he's a person, healthy, fit, yeah, he's pretty healthy, but maybe 0.9, we can put some number. 1 means like perfect, 0.9 is like really healthy. Is Dhoni a location? Well, no. So 0. Does he have 2 eyes? Now, in order to qualify for the international cricket, you need to have 2 eyes. So that's why I'm. So there could be many features. I just handcrafted these features. There could be 10 features here. How fast he can run, whatever. Then has government. Does Dhoni have government? No. That sounds weird actually. So then I put 0. And when I put similar numbers for Cummins, I will probably get similar kind of vector. Here I had 1.9010, 1.87010, kind of similar vector. And I put these numbers randomly, okay? So there's no logic to it. So don't tell me don't ask me how the number for Cummins is 0.87 here. But for Australia, when you put the same number, Australia is not a person, so of course 0. But Australia is a location, so it's 1. Australia has government, so it's 1. And if you have any other countries, they will match the feature vector that I have presented here. So essentially what we did is we converted word into a vector. Vector is just a bunch of numbers, right? And when I converted that, what I found is Dhoni and Cummins are kind of similar. See, 1.9.87 and but Cummins and Australia are not similar, or Dhoni and Australia are not similar, because see 1 0 0.9 0.7, yeah, of course 0.9 0.7. Why 0.9? Oh yeah, maybe healthy and fit meaning for a country is if the country is healthy economically. Australia is doing pretty good, so we can say 0.7. Yeah, so some of the numbers might match, but the entire vector, if you compare the similarity, it is not very similar. So now we found this feature vector for the words, and that could be very effective to solve a variety of problems in NLP task. And this is basically word embedding. So if I look at our original vocabulary, maybe you can come up with these kind of feature vector, where you can say, okay, my features are person, country, healthy and fit, event, gear. And when you have words like bat, well, it's gear, so it's 1. Is it healthy and fit? Like when you train machine learning model, you might come up with these random numbers. So, but overall you get an idea that if it is Australia country, then 0.97. 1 means it's perfect. 0.97, yes, it's like country. So again, I'm not putting 1 here, but showing 0.97 as an example, because these features, by the way, are not handcrafted. Here I handcrafted this feature, but we will be using machine learning model later to come up with these features, and you wouldn't even know what these features are, and it will just magically work. We'll cover more of that in future, but for now just assume there is some magical way of retrieving features from the words when you process a large corpus of text data using machine learning. So using machine learning, you can derive this kind of feature vector, okay? And once you have that, of course, when you look at the last tutorial, we looked at at what word embeddings are. In this tutorial, we are going to look at how word embeddings are calculated. They're calculated using two techniques. One is supervised learning, the other one is self-supervised learning, such as word2vec or globe. In this video, we are going to look at supervised learning technique for word embeddings. In the future video, we will cover word2vec and globe, and today's video will go over some theory on how supervised learning works for word embedding, and then we'll write some Python code as well. In last session, we saw how you can represent words using the vectors like this, where it can represent the meaning of word meaningfully. For example, here I have two cricket players, Dhoni and Cummins, and one of the ways to represent the word vector is by using the features such as person, healthy, fit, location, and so on. And when you do that, what you find is the vectors for Dhoni and Cummins, who are cricket players, they look quite similar. You see like 1, 1, 0.9, 0.87, and so on. Whereas the vector for Australia, which is a country, looks quite different. And you can have number of features that you can use for word embeddings, so that when you're comparing Cummins and Dhoni, which are cricket players, their vectors look same. And when you're comparing the teams, Australia and Zimbabwe, their vectors also kind of look same. Now the question is, how do you come up with these features? It seems very laborsome task. The good thing is neural networks can compute these features for you. These are not handcrafted. When you're comparing the features that you can use for word embeddings, so that when you're comparing Cummins and Dhoni, which are cricket players, their vectors look same. And when you're comparing the teams, Australia and Zimbabwe, their vectors also kind of look same. Now the question is, how do you come up with these features? It seems very laborsome task. The good thing is neural networks can compute these features for you. These are not handcrafted. They are derived while training your neural network. And there are two techniques which I already talked about initially, which is supervised learning and self-supervised. So word2vec and globe are the self-supervised learning techniques. In this video, we are talking about supervised learning technique. Supervised learning and self-supervised. So word2vec and globe are the self-supervised learning techniques. In this video, we are talking about supervised learning technique. What happens in this technique is you take a NLP problem and then you try to solve that NLP problem, and as a side effect you get word embedding. Now the term side effect is very important, and you will see why. Let's say you are doing a food review classification, whether the review of the food is positive or negative. This is a typical NLP task. Now in order to do this food review classification, you have to train your neural network, and after the neural network is trained, you will get word embeddings as a side effect. So the problem that you're solving here for food review classification is almost like a fake problem. You don't care about this problem very much. You care more about the word embeddings. Now you have, let's say, 100 food reviews. For that, what you will do is you will first decide the vocabulary. So vocabulary is all the words that appear in the food review. So let's say you have 5,000 words in your vocabulary. Your goal is to come up with this word embedding vector with dimension 4. It could be dimension 10, dimension 300 is very common. So this is something like trial and error. Let's say for my problem, I'm saying I want a word vector which is of dimension 4. And these numbers will be calculated in such a way that similar word will have similar type of vectors. So eventually your goal is to come up with this 4 by 5,000 embedding matrix, also known as E. So the first thing you need to do is you need to come up with a one hot encoded vector. You all know about one hot encoding already, where for the after, this row is the one hot encoded vector, where there is 1 here and remaining numbers are 0. Similarly for food, 1 is here and remaining numbers are 0. So now you start training your neural network. So what you do is you take your first training sample, just to keep this thing simple. I'm saying my review is only 2 words: nice food. Actually it will be long, like 20, 30, 40 words. Then you come up with a random weights in your embedding matrix. See, this embedding matrix is that 4 by 5000. Okay, let me show you. It is this matrix. Okay, don't confuse it with this one hot encoded vector. So
सर चाय बहुत फॉर्मल चाय
सपोर्टिव होगी तो ऐसे खड़ी होगी,
बहुत है आपकी चाय
गुंडागर्दी वाली होगी तो ऐसे खड़ी होगी,
ऐसे कौन देता है चाय
मॉडल होगी तो ऐसे खड़ी होगी।
बड़ी लाइक सर चाय
यार खड़ा कैसे हो गया? कैसे कर?
हाय सर मैं सर चाय
यार सुनना यार, पूरी फिल्म में एक ही डायलॉग था मेरा, वो भी सारों ने काट दिया। सिर्फ 1 सेकंड के लिए दिख रहा हूँ ना। हाँ सर, ये
तो और क्या था? शुक्र कर तेरी तो शक्ल दिख रही है, मेरा तो दूर से कंधा दिख रहा है, वो भी ब्लर।
सोचा था वकील बनाऊंगा इसका।
छोड़ना यार, एक्सपीरियंस तो हुआ ना, कुछ ना कुछ सीखा ही होगा आपने। चिंता मत कर।
Guess what? मेरा selection हो गया।
क्या बात कर रही है? मेरा भी मुझे आता नहीं।
Search of vector data. बहुत ही क्रेजी चीज़ बना दिया भाई, बहुत ही क्रेजी चीज़ बना दिया मैंने तो। आओ दिखाते तुमको एक सिस्टम। देखो हम लोग मतलब ये कल जाके मैं आइडिया पिच करूँगा कंपनी में।
अच्छा।
देखो हम लोग जनरली जब कुछ सर्च मारते हैं, ठीक है, जैसे अभी क्या है, ये होम ट्रायंगल का ऐप है, ठीक है, होम ट्रायंगल का ऐप है। अगर हमको इसमें ये सैलून है, ठीक है, सैलून एंड स्पा सर्विस, अगर मैं करूँ स्पा, अब कुछ नहीं आ रहा है। अगर मैं करूँगा सैलून, सैलून फॉर मैन, सैलून एंड स्पा, तभी आ रहा है, ठीक है। तो हम लोग यहाँ पे क्या करते हैं कि डायरेक्ट मतलब टेक्स्ट एकदम मैच हुआ,
तभी आएगा।
एकदम टेक्स्ट एकदम इक्वल टू हुआ है, उसमें है वो चीज़ लिखा हुआ, स्पेलिंग मिस्टेक ये वो हुआ, लाइक SAALON लिख दिया मैं,
नहीं
तो
तुम वो बनाए कुछ इससे रिलेटेड, अगर वहाँ पे
तो
स्पेलिंग लिखे तो आ जाएगा, यही ना?
नहीं, वो उतना सिंपल नहीं है, ठीक है। तो अभी अपन मैंने क्या किया, यहाँ पे ये मेरा एक एल्गोरिदम है AI मॉडल को ट्रेन करने का, ठीक है। अरे यार ये क्या खोल दिया मैं, ठीक है, ये मेरा AI मॉडल को ट्रेन करने का, ये services.json जो है, ठीक है, यहाँ पे मेरे पास बंच ऑफ सर्विसेज है, बहुत सारे सर्विसेज हैं, जिसमें उसके बारे में डिस्क्रिप्शन दिया हुआ है कि ये सर्विस क्या है, क्यों है, कैसे है, ठीक है। अब क्या है कि इससे ये एक एम्बेडिंग जनरेट कर दिया मैंने, ठीक है, ये मेरा एम्बेडिंग हो गया, डेटा सारा मिल गया मेरे को। अब जब मैं यहाँ से सर्च के लिए, ठीक है, मैं इसको मतलब डिप्लॉय अभी लोकल पे रन कर दिया, ये प्रोडक्ट पे जाएगा, ठीक है। अब मैं यहाँ पे मैं अगर सिंपल लिखूँगा, मेरे को नहीं पता है, मेरे को करना है, लेट सपोज स्कूल कंप्यूटर, अब मेरे को पता नहीं है कि ये चीज़ है भी कि नहीं है, ठीक है। यहाँ पे इसको भी मैं कॉपी करता हूँ, लेट्स सपोज मैं गलत स्पेलिंग लिख के भेजूँगा, ठीक है। देखो टेक्निकल सपोर्ट फॉर IT कंसल्टिंग, वेब डेवलपमेंट, ये सब मतलब मेरे को एक दे रहा है कि ये सब में से तो कुछ नहीं चाहिए तुमको,
उससे रिलेटेड मतलब
हाँ, उससे मतलब टॉप 5 जो सबसे ज़्यादा मैच करता है। अब होस्ट इन ऐसे में डाल देता हूँ 4 इतना मतलब गलत स्पेलिंग डाल दिया, अरे यार क्या हो गया, अच्छा सॉरी, एक्स्ट्रा मतलब गलत बॉडी, ठीक है। सबसे पहले वही आया क्लाउड होस्टिंग सॉल्यूशन, क्योंकि सिमिलरिटी लेवल देखो, इतना मतलब इतना सिमिलर है इसके, समझ रहे हो। ये टॉप 5 मतलब जो होता है ना, टॉप 5 सिमिलर चीज़ों को वो मेरे को वापस दे रहा है। तो ये इससे क्या हुआ कि अब पब्लिक कुछ भी सर्च मार सकता है, AI बेस्ड सर्च, ऐसे नॉर्मल सर्च नहीं कि बस मिल गया
एक्यूरेट लिखने का जरूरत मतलब,
हाँ, मतलब कहानी भी लिख सकता है,
SHOWN लिख ले,
हाँ,
SWN लिख ले,
हाँ,
SULON
हाँ,
कुछ भी लिखे, मतलब
कि
उसको एक वर्जन सैलून से मिलता जुलता होगा, तो
उसको
उसको
कुछ
तुम
मिलता जुलता मिल गया, तो हम लोग उसको वापस दे देंगे कि भाई तुम ये तो नहीं चाह रहे हो, मतलब नॉर्मल सर्च से नहीं मिल रहा है, तो यहाँ पे ऑप्शन दे दो AI सर्च, कि वो किया तो हम लोग दे दिए। अब इसको कल जाके मैं पिच करूँगा, अगर पसंद आ गया तो बढ़िया है भाई, नहीं आया तो भी बढ़िया है भाई, मतलब देख रहे हो कितना कूल चीज़ है। सिमिलैरिटी के बेसिस पे कि कितना % बायस है। अगर मैं यहाँ पे ये लिखता हूँ ना, लेट सपोज मैं इसको ऐसे करता हूँ, ठीक है, मैं यहाँ पे ये करता हूँ, गलत स्पेलिंग छोड़ो, मैं इसको आगे पीछे कर देता हूँ। सेटअप एंड इंफ्रास्ट्रक्चर, ठीक है, सेटअप एंड इंफ्रास्ट्रक्चर मेरे को नहीं पता क्या है, देखो सेटअप एंड इंफ्रास्ट्रक्चर सिमिलैरिटी के बेसिस पे
वही देगा, मतलब जो उससे जो टॉप जो मैच होगा ना।
टॉप मैं तो अभी टॉप 5 का रखा हूँ, हम लोग ज़्यादा कर सकते कम कर सकते हैं।
टॉप 5 ही सही रहेगा, उससे ज़्यादा करने पर पता क्या होगा ना,
हाँ
ज़्यादा हो जाएगा। टॉप 5 पे मतलब उसमें आ जाएगा,
स्पीड रहेगा,
थोड़ा सिस्टम उससे ज़्यादा करोगे तो फिर उसका कर्सर ढूंढने
वेक्टर मैचिंग, हाँ
फिर उसका टाइमिंग ज़्यादा लेने लगेगा, लोडिंग टाइम। जैसे तुम करो सर्च किए 5 में करना होता है 10 मिनट में करना होगा ना, तो थोड़ा वहाँ पे टाइम लगेगा, तो उससे भी कस्टमर थोड़ा अच्छी परफॉर्मेंस चाहता नहीं देखते हैं।
हाँ,
कस्टमर को चाहिए कि जैसे क्लिक करें
लप लप सिस्टम मिले।
साला पंजाब दूसरा पे चला गया है, लखनऊ दिल्ली सर सरल पहिल का नंबर पर सब चले गए, छठा नंबर
छठा में चल गया।
छठा पे आ गया।
अभी मैच है ना दिल्ली का,
हाँ, है बेचारे। अगर टक्कर हो जाए नहीं, अब क्वालिफाई करना मुश्किल है। सीरीज के बाहर हो गई है, पहली टीम बनी इस साल 2025 की।
वो याद है ना कौन सा, वो जब वो बना था पुणे सुपर जायंट्स, उस समय जो पहला मैच खेला था, मतलब पहला सीजन खेला था, उसमें सबसे पहला टीम था सीएस के बाहर होने वाला, पुणे सुपर जायंट्स में। और जैसे अगला सीजन आया ना तो फाइनल्स में था।
मालिक पता है कौन था उस टाइम?
कौन?
संजय गोयनका, यही संजय गोयनका।
यही था।
यही था उस टाइम, ये धोनी के बाद घोटाला पूरा बोला था।
अच्छा, वही मतलब बता रहा हूँ कि एक साल डाउन है तो अगले साल अब भी हो सकता है।
सीएस को तो बहुत चीज़ सीखने को मिला है, देयर ओवर स्मार्टनेस।
अबे इसका टॉप ऑर्डर साला लंड जैसा।
ये भाई जिस टीम में जडेजा चौथे नंबर पे आ रहा है, भाई दूसरा साला बैट्समैन है कहाँ पे?
वही ना, सैम करन को टॉप में भेजना पड़ रहा है।
भाई वही ना, इनके पास बैट्समैन है नहीं भाई।
जो लिया, ठीक है बैट्समैन लिया इन लोग, लेकिन चला ही नहीं उन लोग।
लिया ही नहीं, जब को बैट्समैन लिया था रविंद्र रचिंद्रा और ऋतुराज गायकवाड़, बस हो गया।
उसमें भी गायकवाड़ गया, दुबे चला नहीं।
दुबे ये लोग बैट्समैन, ये लोग ऑलराउंडर है भाई।
दुबे भाई बैट्समैन भी है, मतलब वो मेन बैट्समैनिंग करता है।
उनका वो नहीं है कि लोग हर मैच में।
मेन पता है आईपीएल सिस्टम भी ख़राब कर दिया है ना, कि ऑलराउंडर को उतना फेवर नहीं है, बैट्समैन या बॉलर को फेवर है। जो इम्पैक्ट वाला रूल ले आया है ना कि एक प्रॉपर बैट्समैन खिला देता है, नहीं तो एक प्रॉपर बॉलर खिला देता है, तो ऑलराउंडर लोग का थोड़ा सिस्टम ख़राब हो गया।
पहले इसके पास भाई ब्रेडन मैक हुआ करता था, एवन फिलिप्स, ब्रेडन स्मिथ, सुरेश रैना, रॉबिन उथप्पा, महेंद्र सिंह धोनी, भाई ये 5 इन लोगों का भाई ये बैटिंग ऑर्डर फिक्स रहता था, सामने कोई टीम को हरा ही नहीं था। इसमें रॉयल विंग्स बना रहे थे ना, सोचो जिस टीम में जडेजा चौथे नंबर पे आ रहा है, उस टीम का बैटिंग का क्या स्थिति है। जडेजा चौथे पे आ रहा है, जस्टिफाई नहीं करता।
Something. AI building AI.
Recently, vector databases got a lot of fame, with companies raising hundreds of millions of dollars to build them and people calling it a new kind of database for the AI era. On the other hand, for many projects, it might be an
It is this matrix. So you want to compute this matrix. So initially you will come up with some random weights. Let's say these are the weights 0.5, 0.2, 0.3. These are randomly initialized at the beginning. Now you take one hot encoded vector for word nice. So you see nice is a third word, so 0, 0, 1. And you multiply it with the embedding matrix. If you know about matrix multiplication, what will happen as a result is you will get this particular column, because to multiply matrix you take the first row, you multiply it with the column, and the column has 1 in the third column, so third column is 1, so you get 0.9 here, because remaining numbers are going to be 0. You do the same thing for the second row, this second row, multiply it with here, the third element has 1, so third element is 1, 2, 3.2, so you get 0.2 here. If you don't know much about matrix multiplication, I advise you refresh your concepts. Then you flatten the vector. So I have two word embedded vectors. Now these are not perfect. Neural network is still training, okay? So these are two individual word vectors for nice and food. You flatten them, so you get like 8-dimension vector. Then you feed it to sigmoid function. It's like a single neuron sigmoid function, which will give you y hat, which is y predicted. You compare it with your y truth. So nice food is positive review, correct? So you compare y hat with your positive review, which is 1. Then you get loss, and you back propagate that loss. Now when you back propagate that loss using gradient descent, these weights will update. See, right now it's 0.9, 0.2, and so on. See, the weights are updated. You see, it was 0.9, 0.2, now 2.3, 1.6. I have put random numbers, friends, but you get the point. So in this pursuit, your matrix, embedded matrix, will keep on changing. Then you take the second training sample, poor quality food. This review is of course negative. So you repeat the same process, flatten out the vector, compare it with how I had, do back propagation, and you again change these weights. So this time you will be changing the weights for poor quality food, like these 2-3 columns. Now you will ask me a question, which is, in the first sample we had only 2 words, the second sample we have 3 words. So the neural network architecture needs to be fixed. It cannot change, right? In the previous one, I had only 8 neurons in my first layer. Here I have 12 neurons. How is that possible? Well, you take the maximum sentence size and you do padding for the remaining words. So let's say my maximum sentence size is 3. When I have nice food, the third word I will say padding. Padding means all zeros, so all zeros you get, all zeros. So that way my neural network architecture doesn't change. The first layer has fixed number of neurons, which is equal to the word embeddings of the maximum length sentence. And you feed all your samples, let's say 10,000 samples, you keep on feeding it, neural network keep on training. Eventually it will come up with a matrix, embedding matrix that can represent words nicely. So if you look at this particular example, nice and good are kind of similar words, so the numbers are kind of similar. You see 0.4, 0.38, 8.1, 8.2. So when you compare these two vectors, it will say, yeah, these two words are similar. Similarly, poor and weak are similar, so it will compute the vectors in a way that those numbers are matched, and if you look at the cosine similarity between these two vectors, it will be close basically. Cosine similarity of 1 means the vectors are close, so it will be like that. So this is the quick theory behind supervised learning approach for embedding metrics. This approach is not very popular nowadays. The more popular approach is word to vec, but I still wanted to show show you how this particular method works, and we'll now write Python code for this problem. Before we begin, I want to say thanks to Jason Brownlee for his excellent article. I'm going to provide the link in the video description below. The article mentions the word embeddings in a nice way, and some of the code I have written is based on this awesome article. The website Machine Learning Master is awesome. He writes so many good articles, so please check it out. Here I have imported the important libraries in Keras and NumPy, and then I'm going to do the food review classification. I have like 10 reviews here, very simple data set, and then 10 labels. So the first 5 are positive reviews, you can figure it out, and the next 5 are negative reviews. So the first thing we're going to do here is, we'll convert that into a one hot vector. So there is a method called one hot, and what that method will do is it takes the review and then you specify your vocabulary size. So let's say if you say 30, it will give a unique numbers. So amazing, it gave 5 number, restaurant it gave 16. So the number will be between 1 to 30. If I say 500, the number will be, the max number will be 500 basically. You see, 256, 39. So this is the vocabulary size, this is the review, okay? And so one hot encoding, again, it's giving the fixed number, unique number, and internally Keras, the layer will convert it to 0011 and so on, okay? So that's number one thing. Now what you want to do is you want to, let's say, initialize vocabulary size. Let's say my vocab size is 30 and I want to encode all these reviews. So see how I did amazing restaurant 516. So similarly, all the reviews, I just want to convert them into one hot encode or encoded vector. So if I write this code, it's a simple list comprehension. I went through all the reviews here. For each review, I created encoded vector. So you will now get this encoded reviews. You can see. Now we saw in our presentation, if you remember our presentation, let me pull that up, that we need padding. So we need a maximum sentence size and we need to pad, okay, the sentence, because see, some sentences are 3 word long, some are 2. So the 2 word sentences we need to do padding and we need to append 0. So let's say my max length is 4, okay, or maybe I can make it 3 as well, okay, and then I will do this. So there is a method called pad sequences in TensorFlow Keras. So I'm supplying all encoded reviews into pad sequences. I'm saying my maximum length is 4. Padding post means pad the reviews towards the end. So now see, towards the end I get zeros, okay. I can do 3 as well, actually 3 makes more sense, okay. So now my padded reviews have a equal size, right? Every vector size is 3. Now the next step would be embedded vector size. Let's say I want my embedding vector size to be 5. Like here I had it 4, like 1, 2, 3, 4. Here I had 4. In my code, let's say I want to do 5. All right. So I did 5. Then I need to create my model. So my model is what, like sequential, okay? And then I need to add my first layer. So my first layer, if you again look at this particular diagram, my first layer will be embedding layer, okay, this particular layer, okay. So embedding layer, for that I have already imported embedding class, and the way embedding class works is it takes a couple of arguments, okay. So what is the first argument? The first argument is vocab size. Then the second argument is the vector size. So vocabulary size is 30. You see 30 here. Then my vector size, after the vector size you will supply the length. The max length is 3, and I need to give it a name so that I can use it later. Okay, and then my second layer is, okay, what is the second layer? Again, if you look at the diagram, once you get embedding vectors, these vectors from your embedding layer, you want to flatten them. You want to flatten them to create this particular vector. So I will just say flatten. And the layer after that is one neuron sigmoid activation function. So it will be a dense layer with a sigmoid activation. Okay, and then I will execute that. Now just to make it more convenient, my X is padded reviews and Y is sentiment, correct? This is my X training samples and this is my labels, Y. So just to make it easy, I'm just putting them in a different variable called X and Y. And I will now compile my model. Now usually we end up using Adam as an optimizer and binary cross entropy because the output is either 1 or 0, right? Like the review is positive or negative. That's why binary cross entropy. And then you can print the model summary, and my model looks something like this. See, embedding, my embedding vector size is 5. In this particular example here, I had like 4. I can make it 4 actually, just so that it matches my presentation. So 4 here, and when you run it, see, the embedding vector size is 4, the max sentence length is 3. All right, once you do flatten, you will get 12. Why 12? Well, see, 4 4 4, so 12. So this will be a 12 vector size, and then there is just one neuron which is dense. And now you are ready to train, so you supply your X and Y, epochs 50, you train your model. So my model is trained. I got an error, by the way, initially because I had another notebook running which was using my GPU, so I had to kill that. Once the model is trained, you evaluate the accuracy. Accuracy is 1. It's a small data set, friend, so it's expected the accuracy is 1. Now, what you do is, see, I mentioned earlier, the sentiment classification is a fake problem. I'm more interested in word embeddings. So while solving a sentiment classification problem, I also got my word embeddings. And word embeddings are nothing but those parameters in your neural network. And you already know, when you have a neural network layer, you can use this method. So you can say model.getLayer embedding. So this is the name we gave here. Now you realize why we gave the name. You can call this method called get weights, and that will give you all the weights. See, these were the weights I was looking for, like 4 embedding. See, 1 2 3 4. So that 4 embedding vector is nothing but this 1 2 3 4. Okay, all right. So the length, okay, let me just store this into this and see what is my length. Well, length is 30 because my vocabulary size was 30. So now if you want to look at word embedding for, let's say, food nice, so nice is 29. Okay, I mean, somehow it gave 29 for nice and food both. If I had increased the word embedding to, let's say, 50 maybe, it would have given a different so you see it gave a different kind of embeddings. So here I'll probably run that. Okay, and the weights are 50 basically. And if you look at the word embedding for nice, the number that we got for nice was 11 and food was 1. So the word embedding vectors for nice, see, nice is 11 and amazing is 3. So let's look at 11 and 3. Okay, So I will look at 11 and 3. So weights 11 and weights 3. So 11 and 3. Okay, what is 11 and 3? So 11 is nice and 3 is amazing. Now, these two numbers are not, these vectors are not same. Actually, nice and amazing are kind of similar words. So you would think these numbers should be same. But our data set was very, very small. Okay, if you run it on a huge data set, maybe you will find this vector to be similar, and you can compute the cosine similarity of these two vectors. But at least this coding session gave you an idea on how Keras embedding layer works. Many times people have a question, how Keras embedding layer works. So the way Keras embedding layer works is during the process of solving the NLP task, it will compute the embeddings on fly. Now the other way of computing embeddings is you can save this. Like usually what people do is they compute this, they save it to a file. And later on when you want to perform a different type of task, you can load saved embeddings from that file into this layer, okay? And that's what this awesome article goes through. It talks about loading the embedding vectors from file as well. So it has a section number. 2. Word-to-vec is a technique in computer science that allows you to do mathematics with the word. For example, you can give this equation to a computer, which will be something like king minus man plus woman, and computer will tell you the answer is queen. What? Isn't that mind-boggling? This is super cool, and it works really well, and I'm not making this up. So how can computer do this? Well, think about this. Computers don't understand text.